Alkenes will undergo certain reactions. Now what we're going to do is we're going to look at some reactions, and we're going to see how these reactions occur on the double bonds, and then we're going to look at specific molecules and what results when the reaction occurs. We have certain types of reactions that alkenes will undergo called addition reactions. And what is shown right here is a typical addition reaction where before you have a double bond and a separate molecule. Then after the addition reaction occurs, that separate molecule has broken apart and added across the double bond. And so you can see the double bond breaks, and you have bonds being formed to either side of that separate molecule. Hydrogen is one molecule that will add across a double bond. Now you have to have a catalyst in there for this to occur, and so when hydrogen is in the presence of double bonds, it doesn't normally add across that double bond. You have to have a special metal catalyst in there. It's usually a palladium catalyst, and it's written over or under the arrow. And when you see hydrogen as one component, a double bond, and then the metal catalyst over the arrow, then you know what happens is the hydrogen will break apart and add across that double bond, as you see in this example. We call this process hydrogenation, and you probably recall hearing partially hydrogenated fats and things like that. We'll talk about that later. The product of hydrogenation is an alkane, because after the hydrogen adds across the double bond, you can see that it is a saturated set of carbons. The double bond is gone now, and so now we have an alkane. Here's an example of the hydrogenation of ethylene. Ethylene has that double bond. There's hydrogen as the other reagent, and then palladium is written with the arrow, showing that it is a catalyst. And then afterwards, the hydrogen is now part of the molecule. It's been added across those two carbons that were in the double bond, and now we have ethane. So we went from an alkene to an alkane. So here's the cyclopentene. Now, to figure out what is the product of hydrogenation, we know that in hydrogenation, two hydrogens are added across the double bond. So we'll write the with the double bond being gone, and we're not writing the hydrogens in there, but we know they're there because of knowing how many hydrogens must be on those carbons for no double bond to be there. Now we're going to write the conditions that cause it. We can write hydrogen above the arrow, or you can write it so that it says cyclopentene plus hydrogen, and then have the palladium by itself with the arrow. It's written both ways. Another molecule that will add across double bonds is water. If you look at this reaction, we call it hydration because water adds across the double bond, and I've written the water stretched out so you can see what bond will break, and you can see the carbon-carbon double bond changes to a single bond, and then you have a hydrogen on one atom, one carbon, and a hydroxy group or an alcohol group on the other atom. The hydration requires strong acid as a catalyst, so it's written above or below the arrow, and the product that forms is called an alcohol. So here's an example. Ethylene is a compound with a double bond in it that can be hydrated. If we treat it with water and sulfuric acid, the hydrogen in the water will add to one carbon, and the hydroxy group will add to the other carbon. What results is something called ethanol. So now what I'd like you to do is to try this problem, and after you get through, check your answer and see if you've gotten it correct. Remember that water is added across a double bond when you have hydration. Remember, what are the conditions that cause it, meaning what catalyst is needed. First thing to do in this problem is to start with the reagent, 4-methyl-2-pentene. So you draw 4-methyl-2-pentene. Then you're going to figure out what would be the product of hydration. The product of hydration is going to be an alcohol, and a hydrogen, which is not written here, it's understood, is put on one carbon, and the hydroxy group is put on the other. But you might have said, I didn't get that. I got my hydroxy group on the other carbon. And that is correct also. You might have put your hydroxy group on the third carbon rather than the second carbon. And that is a correct answer. In fact, both of these compounds are made. The conditions that cause this is sulfuric acid and water. The water is a reagent, and it can be written as plus the 4-methyl-2-pentene, or it can be written with the arrow as I've shown it. Okay, here's another problem for you to try. What is the product of treating 4-ethylcyclohexene with hydrogen and palladium? And what is the product of treating 3-methyl-3-hexene with water and sulfuric acid? Figure out both of these problems and then go and check your answer afterwards. The first thing that you need to do in determining what is the product of treating 4-ethylcyclohexene with hydrogen and palladium is to draw the 4-ethylcyclohexene, which I have shown here. Next, you know that you're going to be adding hydrogen across that double bond, so your product will be with the double bond. So you will write this as your product. The conditions needed for this are hydrogen and palladium, and again, instead of writing the hydrogen over the arrow, you could have written it as a reagent with a plus and then hydrogen. Both ways are acceptable. What is the product of treating 3-methyl-3-hexene with water and sulfuric acid? The first thing that you need to do is draw the 3-methyl-3-hexene. After drawing 3-methyl-3-hexene, you need to then write down water and sulfuric acid as your condition, and then you're going to draw the product. Now, I drew the product so that the hydroxy group is on the third carbon because that's what we find actually happens. I would not consider it incorrect. I won't count it as wrong if you had put it on the fourth carbon. There actually are some rules about how water adds across double bonds that is beyond this course, so you don't have to worry about that. I drew the correct product, but I would consider either products to be correct in grading an exam. We've been talking about saturated and unsaturated fatty acids, and so now let's look and see how this applies to margarine or butter. Margarine is a plant source product, and butter is an animal source product. The fatty acids that come from plant sources tend to have double bonds in them, cis double bonds in them, so they're oils, and they tend to be good for us. Animal source fats, or fatty acids, tend to, or will all be saturated. So if you're getting your fatty acid from a meat, or from milk, or from butter, you will find that those all are saturated fatty acids, and they're bad for you because they will deposit in your arteries, in your heart, in your legs, and in your head, causing heart attacks, strokes, and blockages of your arteries in the lower part of your body. And so they're unhealthy for you. If we look at Margarine, we might think that it is good for you because it's a plant source product, but we need to look at how margarine is prepared by manufacturers. When we make margarine, we are taking an oil and making it a solid. To do that, we do something called partial hydrogenation. We start the hydrogenation process, but we don't add enough so that all the double bonds have been hydrogenated. Now we know that when we hydrogenate a double bond, that part of it becomes like an alkane or saturated. So if we were to completely hydrogenate a plant source oil with a cis double bond in it, it would become a saturated fatty acid. But when they partially hydrogenate, what they do is they don't add enough hydrogen to make all the double bonds be hydrogenated, and when the carbon-carbon double bond comes off the catalyst without the hydrogen there to saturate it, it comes off, and it's usually the conformation has been changed from cis to trans. Now, the saturated fatty acids that would result from hydrogenation we know are bad for us because they're going to be the same thing as animal fats and deposit in our arteries. But also, we have some fatty acids that are coming off as trans fatty acids rather than cis fatty acids. The cis are healthy for us, but trans are shaped very much like the saturated fatty acids. They're long and ropey, and they stack well, and they deposit in your arteries just the same as saturated fats. So margarine, butter, they really have about the same effect on your health. It is the oils, like olive oil and things like that, that tend to be good for you. The last type of thing that we're going to look at in this chapter are the aromatic compounds. Aromatic compounds are a special unsaturated compound. If you look at this compound we call benzene, which has 6 carbons and 3 double bonds all in a ring, it is a very special compound because when you arrange those 6 carbons and 3 double bonds in a ring like they are arranged, it does something special and becomes very, very stable. These stable compounds are called aromatic. It has nothing to do with their aroma. The first ones they investigate were tending to have a smell associated with them, but now we refer to aromatic compounds as anything that has this special ring system of 6 carbons and 3 double bonds. This is a very flat compound. All the carbons and all the hydrogens are in a plane like they were sitting on a sheet of paper, and there's 120-degree angles in all the bonds. Okay, that's the end of chapter 11. Remember to do the in-text problems as you read and do these end of chapter problems. I will be posting an online quiz for you to try.